Ladies and gentlemen, this is Ghulam Mustafa Abru. I'm a PhD student at Department of Electrical and Electronic Engineering, University Technology Petronas. And today I'm going to present my one of the conference papers at ICSIPA 2021. Let me just share the screen first. Yeah, so the topic of today's gathering is modeling, controlling, and stabilization of an underactuated air cushion vehicle. And the contents in which we can just go with the flow of this presentation is in front of you. I will be describing some basic terminologies like what do you mean by air cushion vehicle and under actuation. Then we will discuss some literature review along with dynamic model of air cushion vehicle. In addition to that, we have proposed a comparison between two control designs. One is proportional, integral, and derivative, and second one is actually enhanced version of PID, in which we have amalgamated fuzzy logic control design with PID. We'll discuss the results and discuss that how fuzzy based PID is much more efficient as compared to conventional PID. We'll conclude our topic along with acknowledgement and some references. Sorry. So as you all know that under actuation is the topic. So under actuation is the phenomena in which we have a dynamic system or any mechatronic system that has less number of control inputs as compared to their degree of freedom. So in this way, if we have such mechatronic system, it can move freely to any degree of it can generate any degree of freedom. But with the less number of control inputs, it will be very difficult for him to get to stabilize itself on particular trajectory or path. So with the unmodeled dynamic factors, again, it will be creating a more problem for that particular mechatronic system. So over here we have a mechatronic system that is known as air cushion vehicle. Commonly it is known as hovercraft that can be operated on earth surface and water surface and on ice as well. So the idea of this entire paper is to produce the dynamic model of air cushion vehicle and then to impose or to implement the PID, the conventional proportional integral derivative controller design with fuzzy based PID technique so that we can see the results and compare with each other that which control design is better for operating a hovercraft or air cushion vehicle. So, ladies and gentlemen, this is the construction shown in figure 1. We have plenum chamber, we have lift propeller, and we have air lubricated layer. What happens actually when we turn on our hovercraft? It basically generates an air in the plenum chamber, and gradually this air uh, it just actually create an equilibrium. Once the equilibrium is created, it will rise up from the surface and it will start hovering. Whereas if you can see, if I just point out this wing, actually it will direct this particular hovercraft to turn left or right. So most commonly, people cannot differentiate in between the hovercraft and the airboat. This is the airboat. So major differences are quite similar. That air cushion, enable hovercraft to transfer heavier goods from one place to another place. It's like manipulating from the one object from another. The most common difference as far as in between airboats and hovercraft is the most of the rescue operations, whereas hovercraft is used as a transportation system, specifically for military operations and training. Moreover, in terms of both vehicles, airboats are easier to maintain because of standard motors, whereas in hovercraft, the maintenance of air cushion is very humongous task and very difficult. So this is the actual difference. So this is all about the introductory topic of our hovercraft. If we see the literature review, what was the need actually? So if you can see over there, there are many pros and cons of different control designs. Some are producing the extra noise. Someone like implemented, but our hovercraft cannot reach at the particular target, and in some of the cases we were unable to regulate the proportional, integral, and derivative gains. So after concluding all these pros and cons, we were in a position that what type of control technique we should produce, and in this regard, we implemented fuzzy-based PID control technique. If you see the dynamic model, this is the state space model that we drive. You can see figure number 3, exertion of two forces together. Figure 4 is the hovercraft model in XY plane. So if you can see over here, the entire state space model is derived using simple mathematics, and then this is the control design slides. The figure 6 actually shows the conventional or very traditional control diagram for PID for our underactuated ACV, that is air cushion vehicle. If you focus on figure 7, you can see that the same block diagram of PID is divided into three types. Like we have fuzzy tuner for one PID, fuzzy tuner for second PID, fuzzy tuner for third PID actually. In this way, all KP, KI, KD are tuned actually, and then they will be supplied to, provided to a dynamic model of holonomic hovercraft or non-holonomic hovercraft or underactuated hovercraft. So, ladies and gentlemen, by seeing these results that are in figure 13, they are actually of PID. You can see that we have pitch, yaw, and RUV. These are the velocities actually. So you can see the RVU, they have been denoted like in a blue color, where we have pitch and yaw. These are the angular acceleration. So you can see them that they are actually settled somewhere in 10 seconds over here, 10 seconds and 10 seconds, which is the convergence rate actually. But if we just show you or demonstrate you the results for FPID, the velocities are similar, but if we see the roll and the pitch and yaw, because roll cannot be happened in air cushion vehicle. So if we see like for the velocities for uh, our air cushion vehicle, and by using FPID, you can see that they have been reduced to 1 and 2. So this is how fuzzy-based PID works actually. We have also demonstrated some transient and steady state parameters in table 6, which can be witnessed over here. If we see like settling time for PID, it's like 9.87 seconds, which is approximately 10 seconds. If you see FPID, you can see that it is 1.534 seconds, and there is no any overshoot. But in PID, we really witness the minor overshoots. The convergence rate is faster in FPID as compared to PID. So the conclusion is quite simple. We were intended to show the performance of FPID over under-actuated air cushion vehicle, which we demonstrated in some of our graphs, and we concluded that fuzzy-based PID is good. But in addition to this, I would like to say that when we implement fuzzy-based PID, in practical case, they do take some of the time. Why? Because we have several parts within fuzzy, like we have triggering of rules, we have computation of COG, and then it actually regulates our KP, KI, and KD. So due to this particular, inference, fuzzification, and defuzzification, and these parts, our system stimulate lately. It's an admitted fact. So this is one of the concerns of fuzzy-based PID, which we are using. And for the information, I would like to say that the control technique that we have used is Mamdani, actually fuzzy technique, not Tagasugino. So it also varies. It depends on what type of control technique you have used, Mamdani or Tagasugino. So again, it's we are actually working on this thing, and we'll come up with more detailed simulations on it. So till this, we have presented this work that fuzzy based PID is more favorable as compared to PID. So here I want to grab the moment and acknowledge my sincere thanks to the support of Center of Graduate Studies, University Technology Patronas, for providing me the chance to pursue my doctoral studies in the same uh, actually domain. In addition to this, I would like to thank for Research Management Center for supporting the publication by providing the paper charges under the grant number 015 LCO299. These are the references, ladies and gentlemen, and in this way, the presentation comes to its end. I open the floor for question and answers. Apart from that, this is my email address. One can contact for research collaboration or any extended research work. Thank you. Thank you so much.